I'd like to welcome you all to the Nag Memorial Lecture Series. This is the first in a series of 3 lectures that we have. The first is now. Tomorrow we have one at 3:30, and Thursday it's in the morning at 11:30. And it'll end with a public lecture at 3:30 p.m. on Friday. So I hope you can make it to all of them. So our Nag lecturer this year is Professor Shiraz Bhinwala from TIFR. He's a string theorist primarily. He's won numerous awards. Let me list a few of them. So he has won the ICTP Prize in 2010, the SS Bhatnagar Prize for Science and Technology, which is the highest science award in India, in 2011. And he's awarded the Infosys Prize in 2013. And more recently, he's won the New Horizons in Physics Prize, also called the Fundamental Physics Prize, for his contributions to fluid dynamics and relativity. He's done numerous pioneering contributions to string theory, quantum field theory, and so on. And we're very pleased that he is accepted to be the Nag lecturer this year. So I don't want to waste too much of your time. And please request Shiraz to take over. Thank you.
Thank you. It's really nice to be back at IMSC. And it's a great honor to be giving these lectures, and thank you for the invitation. Okay. My lectures will be about the effective classical dynamics of event horizons. And let me spend 2 minutes telling you about what this means before I go on to a list of contents of a more detailed list of contents of the talk. As all of you know, it's a striking prediction of the general theory of relativity, which is 100 years old now, that there exist black holes. And black holes are characterized by these interesting surfaces, event horizons, which separate points that can communicate with infinity from points that cannot. Okay. Now, all of us are familiar with the simplest black hole solutions. The Schwarzschild solution, the charged versions of the Schwarzschild solution, maybe the solution's moving a little bit. Okay? But the solutions we're familiar with are black holes once they've come to rest, once they've equilibrated. Okay? The Einstein's equations, these very easy to state equations, capture a lot of really interesting dynamics, even in the absence of additional matter fields. Just the pure vacuum Einstein equations capture a lot of interesting dynamics. And very roughly speaking, the dynamics of this theory can be broken up into 2 parts. That dealing with interacting gravity waves, and that dealing with black holes. Okay? And there's very rich dynamics in the black hole sector. For instance, as an example of the richness of the system, consider 2 black holes that are separately Schwarzschild type black holes, but bang into each other. Okay? You can ask the question, what comes out of this process? Okay? Now, as many of you know, this question has been subject to a great deal of numerical investigation over the last 20 years. And the problem of numerically solving what happens when you bang these 2 black holes together has been more or less solved. But the numerical program is a very intensive one. You know, simulating one of these collisions takes weeks on very high-powered computers. Okay? So you might. Okay, so this tells you that the dynamics of black holes, the dynamics of event horizons in situations where you haven't settled out equilibrium, it's a very rich subject. It's so rich that usually when we want to ask questions of interest to us, we resort to numerics. Okay, so the kind of question I'm going to be addressing in these lectures is, are there situations in which you can try to understand black hole dynamics, interesting black hole dynamical situations, in a way that is analytical, okay, without resorting to numerics or postponing the resort to numerics, are there situations in which you can simplify the dynamics of black hole event horizons so as to be able to word them in a more intuitive or in a different language without throwing away their essential physics? Okay? By the end of my lectures, I will come back to this question of black hole collisions. But okay, so this is the kind of motivation behind my talk. A couple of my lectures. A couple of disclaimers to start this off. Everything that we will discuss in these lectures is purely classical. Okay? We will be discussing just classical general relativity, trying to understand classical general relativity in situations involving event horizons a little better, relating it to other things. Okay? Most of my talks will be focused on what we can say about black holes in the limit of a large number of dimensions, where it turns out that there is a nice effective reduction of the effective event horizon dynamics of these black holes. But to start these talks, maybe about 3/4 of this lecture will be about a much older, better understood subject, which forms a template for our investigations of large D black hole dynamics. The subject is called the fluid gravity correspondence. Okay, and I'm going to start my lectures reminding you of this fluid gravity correspondence, something that was developed almost 8 years ago, because it's a very nice example of effective horizon dynamics, how it's developed, and what you can say about it. Okay, so this is my plan for the lectures. We will start these lectures. Maybe about 3/4 of this lectures will be on the fluid gravity correspondence. Okay, then we will move on to studying black holes in large D. Okay. This will be with and without charge. And the bulk of the lectures will be on this part, which will be on reformulating the dynamics of black holes in large D as membrane equations. So we will reformulate the dynamics of black holes in large D as the equations of a membrane, a codimension 1 membrane, non-gravitational membrane that propagates in flat space. You'll see what this means and how we get to it as we proceed. Okay, this is roughly the plan for my talks. At any point through the talks, I would love to be interrupted by questions or comments. If you have any questions or comments now, please feel free. Okay, one last motivational comment before we start. This question of what happens, the classical dynamics of event horizons. You might ask, why do you want to know? Why are you interested in classical dynamics of event horizons? Well, part of the reason for the interest is the results. As I will show you, the classical dynamics of event horizons can be reformulated in different non-gravitational terms, which is sort of interesting. Okay, makes connection between Einstein's equations and other non-gravitational partial differential equations of interest to physics, as you will see. Okay, but part of the motivation is actually, and unusually for a string theorist, practical. And the practical motivation goes as follows. As you might know, there's this experiment called LIGO, which hopes to detect gravity waves in a few years. And let me just go out on a limb and tell you what I've heard from my LIGO friends. I can't. If you ask me to back any of this up, I will refer you to them. But these people tell me that they've made estimates for how many black hole bangs they will be able to see per year if LIGO works well. And their estimates range from 100 to 1,000 a year. Okay? This sounds like a crazy figure. But it's less crazy than you think, because a black hole bang emits a huge amount of energy. So even when this collision happens far away, you can see it. Now, LIGO was very interested in all kinds of astrophysical events that give rise to gravity waves. But they, sorry? Not necessarily. Not necessarily. Some of them would be head-on, some of them will be not. Okay, very few of them will be bang head-on. Yes. Okay. Now, LIGO is particularly interested in black hole collisions for the following reasons. Since these collisions are such violent events, you can measure them, hopefully, even when they occur very far away. Okay? So when they occur very far away, they're happening at very large redshift. So these events can be used to probe large redshifts, just like supernovas could be, in order to see the acceleration of the universe. But you know the difference between black hole collisions and supernovas, that black hole collisions are extremely clean events. In the sense that, provided the black holes you started with were clean, they didn't have some stuff around them, which generically you expect after a while, these collisions are completely determined, what you will see from these collisions are completely determined by Einstein's equations. Okay? There's no chemistry modeling, no fudge parameters in the game. Compare this to supernovas, which are very violent events, but very poorly understood. Okay? So these are events that you have complete theoretical control over. So if you see them, the theoretical uncertainty about what exactly you're seeing should be zero. Okay. Well, there's an accretion if there's some nearby star, which is, this is sucking stuff in. Okay? But there will be some black holes that are just there, presumably. Okay? Okay, those are second, yeah. Hopefully there will be some very clean events, such as black hole. Okay, so these events are so theoretically clean that at least some LIGO people speculate that our best measurements of the acceleration of the universe, let's say 10 or 15 years from now, will come not from supernovas but from black hole collisions. It's a great fantasy. You've not seen any gravitational waves. That's what they estimate. I cannot answer. I don't know well enough. I don't think anyone really knows. I think you'll have to see. Okay, but I just want to say that this is taken seriously enough that a lot of people in LIGO, I know Ajit at ICTS, from whom I get much of my information, is spending a lot of that time trying to make computer programs to back calculate what, if you see gravity radiation, back calculate the parameters of the black hole collision that it came from. Okay? So it's serious work. They're trying to make computer programs to do this to help with LIGO and counts. But what do they use when they do this? What they use is some post-Newtonian approximations to start with, quasi-normal modes to end with, and numerics to take them in between. Numerics are very difficult. So you can't do numerics for all parameter sets. Okay? So you can only sample numerics and then interpolate. So basically, a lot of the theory that they're guided by is numerical. And this seems like a not ideal situation. Seems like we theorists should be able to do better to help them to try to understand what will happen when two black holes collide. This is part of my motivation. Okay? And you'll see how far we have reached so far in addressing it by the end of the talks. Okay, so that's it for motivation. I'll soon start the actual physics. Questions or comments before we proceed?
The details are not required because there are no pairs for the...
Because black holes are very clean objects. The objects are clean, and the equations that govern the dynamics are R mu nu equals 0. Or if they have charge, R mu nu equals, Einstein-Maxwell theory. So these are the equations we think we know 100%. The objects we think we understand 100%. Very different from supernovas, which are very dirty objects. Okay? So this is part of the motivation. There's some practical motivation which we may or may not eventually make contact with, but okay, for whatever it's worth. Okay?
Parameter, relative velocity, masses, and charges.
And angular momenta of the. You see, because of the angular momenta, there are quite a few parameters, because the angular momenta also have a direction. So if you want to cover parameter space, you need to cover a quite high dimensional space, which, given the complexity of the numerics, you cannot do this densely. So if you just take a numerical point fitting view, that's not good enough. So people try to do various other clever things. Okay? But these clever things are, as far as I understand, number fitting things, function interpolation techniques. Would be nice to have guidance from physics rather than. So that's part of it. Can you find some? Yeah. Okay, good. So, as I've said, what we want to do is to try to understand classical event horizon dynamics. Okay, now, it's good to have a goal, but sometimes your goals are unrealistic. The actual phenomenon of black hole collision in 4 dimensions, when you look at what comes out of a computer, for instance, such a complicated phenomenon. Okay, there seems unlikely that you'll ever find an analytic solution for what's happening. This is true of most problems in physics. Most problems in physics, if you want to get all details right, you'll never be able to do it analytically. Okay? What is the job of a theorist in such a situation? If we don't allow ourselves to call numerics theory, just for a moment. Okay? What is the job of a theorist in such a situation? Well, there's a time-tested kind of job, which is try to populate the space of models that you're interested in with solvable points. And then try to do perturbation theory away from these solvable points to try to learn something about them. So this is the kind of point of view we're going to take. Okay? What we're going to try to do is to look at event horizon dynamics and try to look at extreme limits of this dynamics in some parameter or the other, where we can solve or either solve or recast this dynamics in terms of something simpler. Okay? And then we can try to discuss how you can improve on what you do in this extreme limit in perturbation theory. That's the kind of point of view I'm going to take. Okay? So the first example of this, the historically successful example of this thing 8 years ago, is called the fluid gravity correspondence. And this example I'm starting my lectures with, not because it makes direct contact with this black hole collision. Okay, it doesn't. Okay, I'm starting it as an example of event horizon dynamics that we understand very well, which will form a template for the attempt that we will make. That's largely the attempt for actually understanding this kind of stuff. Okay, it will be very useful to have this at the back of your mind, because everything we do is motivated by this picture. So for this reason, I'm going to give you a brief and very quick review of the story of the fluid gravity correspondence. Okay, good. Please. Yeah, what does it mean to solve? We're looking for the best we can do. Okay, you'll have to see as we come along.
To make contact with this redshift, you need some power versus frequency or something. Is that
what we want is some way of predicting what comes out when 2 black holes bang, for instance.
What does that mean? Metric?
Yeah, metric, the gravity waves that you measure in a detector very far away, the electromagnetic waves that come. Function of frequency and time, and what you see. That's what we would want eventually. We want to be able to predict what somebody in LIGO will see. Okay, great. Other questions or comments? Okay, so let's move on to the study of the fluid gravity correspondence. The study of the fluid gravity correspondence takes us quite far afield from this black hole merger, as I've explained. It starts with the study of Einstein equations with a negative cosmological constant. Okay, so the equations we're going to study in this first part of the talk are r mu nu plus d minus 1 g mu nu is equal to 0. Okay, this is Einstein's equations with a negative cosmological constant. Okay, and I've chosen the value of this cosmological constant to be a pure number, a convenient pure number, simply by changing my unit of length. Okay? R mu nu has 2 derivatives. G mu nu does not. So the number between these 2 terms has no meaning, no dimension independent meaning. So I can choose my units to set it to any number I want, and I've chosen it to be this. And why are we studying Einstein's equations with a negative cosmological constant? Of course, the motivation for that was the ADS-CFT correspondence. We'll come to the motivation in a little bit. But at the moment, I'm just going to present this as an example of horizon dynamics, so we'll just forget about motivation for a while and study these equations. Okay. Not what I say now. However, what I say about large D will allow generalization to negative to many things, including flat space. Okay. So here you should think of this just as an illustrative example of the kinds of things we can do. And you'll find, it has some interest. Okay. But for the purpose of these lectures, just an example, a technical example. Okay. So R mu nu plus D minus 1 G mu nu is equal to 0. These are the equations of motion we study. Now, these are Einstein's equations for the negative cosmological constant. And it's well known that these equations admit a famous solution. It's called ADS space. Okay? We will be, through these lectures, mostly interested in what's called the Poincare patch of ADS space. So ADS space written with planar horizons if you're a general relativist. And I've chosen this number here so that the metric that is a solution to these equations can be written as dr squared by r squared plus r squared eta mu nu dx mu dx nu, where eta mu nu is the metric in Minkowski space. Okay? It's a d minus 1 dimensional Minkowskian metric. Okay? I will sometimes refer to these x coordinates as field theory coordinates, and this r coordinate as the radial coordinate. Those of you who are familiar with the ADS-CFT correspondence know why I say that. If you're not, it's just nomenclature, terminology. Okay, so this is ADS space, and for those of you who are not, I know 3/4 of this audience knows this in their sleep, but for those of you who don't, just let's look at the space for 2 minutes. There are, there's this interesting region, R goes to infinity. Okay, R goes to infinity. So you can think of this ADS space as slices, these planar slices, with a stretching factor, or warp factor, that depends on which slice you're in. Okay, when you go to R goes to infinity, this warp factor goes to infinity. Okay, this is called the boundary of ADS space. Okay, there's a lot of room in the boundary of ADS space. Okay, and this translates into saying that suppose you've got this ADS space and finite energy configurations around ADS, that can change what's happening in the bulk at finite values of R, but cannot change this metric as R goes to infinity. Okay, so we will be studying solutions to these Einstein negative cosmological constant equations that are not as boring as ADS space, but reduced to ADS space as R goes to infinity. Okay, at the boundary of ADS space. Okay, very good. Now, this is one class of exactly known solutions to these equations. But there is another class of exactly known solutions to these equations, which are very interesting solutions. Again, the string theorists of the audience know this very well, but for everyone else and for pedagogy, these solutions are what are called black brain solutions in ADS space. Okay, now everything here I've set up an arbitrary dimensions. I'm going to restrict my attentions to d equals 5 for the rest of this pedagogical fluid gravity part, not because it's necessary, everything has been worked out in arbitrary dimensions, but just because I want to emphasize that this works in a particular dimension. Whereas the main topic of my lectures will be working in an arbitrarily high number of dimensions. So I don't want to carry d around so that you don't get confused between these two. Okay? So d is 5, there's a radial coordinate and 4 spatial coordinates. The field theory coordinates are 4 in number. 4-dimensional field theory, boundary field theory. Okay, so the other well-known exact solution to these equations is the following. ds squared is equal to dr squared by r squared, 1 minus pi t by r to the 4, minus dt squared into r squared into 1 minus pi t by r to the 4. Plus dxi squared into r squared, I is equal to 1 to 3. Okay, now look at the solution. First note that if I put t is equal to 0, then this solution reduces to this solution, because this plus this is this stuff. And dr squared by whatever is just dr squared by r squared. That's clear, right? So this is a one-parameter deformation of the ADS solution, the parameter being t. The pi is a constant, of course, it's 3.14 whatever, and t is a constant, some arbitrary number in the solution. This is an exact solution to Einstein's equations. Now, I want to interpret the solution. What is this solution? Okay? This solution is sometimes called a black brane. The solution is sometimes called a black brane, and the reason it's called a black brane is as follows. You see, as you know, if you just make the analogy with the Schwarzschild solution that most of you know about, the Schwarzschild solution looks very, very similar to this solution, Schwarzschild solution in flat space. Some details are different, but there's a dr squared by some function of r which blows up at a particular point, and a dt squared times function of r which goes to 0 at the same point. Okay? Now, in that situation, as you all know, the point where this thing goes to 0 is an event horizon. The same is true here. Okay? So r is equal to pi t is an event horizon of this space. Now, this space, though, differs from the Schwarzschild black hole in a very interesting way. Thank you. Is the event horizon. Okay? This space, though, differs from the Schwarzschild black hole in an interesting qualitative way. The interesting qualitative way is, what is the geometry of this event horizon? In the Schwarzschild black hole, the event horizon surrounds a point. It's a sphere. Here, this event horizon happens at a particular r, but is translationally invariant in the xi and t coordinates. Okay? So if I think of this ADS space in some caricature, where r goes up like this is the boundary, that's r goes to infinity. Okay? The field theory directions, the x directions, you have translational invariance in these field theory directions. The x directions stretch along this way. Okay? The event horizon occurs here and is translationally invariant and infinite. Okay? So this solution isn't a black hole. It isn't a solution in which an event horizon surrounds a point. It's a black brane. It's an event horizon that is translationally invariant. Okay? It's very interesting, but a well-known solution of Einstein's equations. Okay? Now, the fact that we've got these solutions which are not spherical, but planar, allows us to do something that we couldn't do for Schwarzschild black holes at finite d. That is to ask, what is the long wavelength dynamics? What is the long wavelength dynamics of such event horizons? We couldn't do that for Schwarzschild black holes because it makes no sense to ask what's the long wavelength dynamics of an object on a sphere. The longest wavelength is the size of the sphere, and that turns out to be not long enough in general for anything interesting. This happens for Rindler space also, and so perhaps you could play an interesting game there. Okay? But this allows you to ask this question. Is there anything interesting at low energies, long wavelengths, involving these event horizons? So it's a new situation. The thing that allows you to ask the situation is this cosmological constant that gives you these nice, stable, translationally invariant solutions. And it allows you to ask the question of what's the long wavelength dynamics of solutions involving these event horizons. Now, let's suppose we were very stupid. Or just we weren't experienced, and we want to start addressing this question. How would you go about it? This is roughly the historical path. Okay? It's what people did in the early 2000s. The first thing that you could do is to try to probe the linearized excitations about the system. That's a natural thing to try to do. Okay? So what people tried to do was to compute the spectrum of what are called quasi-normal modes. Quasi-normal modes around about these black branes. So what are quasi-normal modes? Let me give you the definition in ADS space. See, quasi-normal modes are answering the following question. Okay, they're answering the following question. I maybe should draw a Penrose diagram. Let me take 2 minutes to divert to telling you about quasi-normal modes, first in flat space, then in ADS space. I'm doing this first in flat space because we'll need this when we get to large D. Okay? Suppose you've got a black hole in flat space. Okay? It's just sitting there. How do you excite it? Well, one way of exciting it is throwing something into it. If you throw something into it, the black hole will get excited depending on what you throw into it. But suppose you've thrown something into it and then you stop throwing things into it. Now the black hole's already in a slightly excited state. What will it do? You expect it to settle down. The quasi-normal modes are the linearized excitations that describe this settling down process of the black hole into its natural ground state, starting from an unnatural excited configuration. You've got this unnatural configuration by hitting it, you're throwing something into it. Fine, you don't care how. So what's the idea? The idea is you've thrown something into it, but then you stopped. You want to describe the settling down process. Because you want to describe this settling down process in which you're not throwing anything more into the black hole, the boundary condition you put at infinity is that there's nothing going in. There may be things coming out, because in the process of settling down, the black hole may emit gravitational waves. So you allow things coming out, but not things going in. No forcing of the black hole. Okay? The other boundary condition that you put is that things go into the black hole, you know, the natural boundary conditions, ingoing boundary conditions at the event horizon. You get in all kinds of trouble if you put something else. Okay? So quasi-normal modes are solutions to Einstein's equations, solutions to the linearized Einstein's equations around a black hole, okay? Subject to these two boundary conditions. No ingoing modes at infinity, and only ingoing modes at the horizon. So at infinity, things are going out. At the horizon, things are going in. These are your boundary conditions. Okay? I'll tell you about the boundary conditions in ADS in just a minute. They will change. You put some other boundary condition here. I'll tell you about that in a minute. Okay? I'm first starting with flat space and then. Okay. So this is just a 2-minute interlude on quasi-normal modes. Okay. So now, you see, what do you expect about the spectrum of quasi-normal modes? This outgoing boundary. See, every time you're solving some equation like a wave equation, Einstein's equations linearized are wave equations. You've got two boundary conditions. This is something like a particle in a box problem. Okay, you've got some box, you've got some boundary conditions, you're solving a wave equation. Okay? Now, the things that are really crucial to determining the spectrum of the theory of these excitations is A, the size of the box, B, the nature of the boundary conditions. Okay? It looks like the size of the box is infinite because you're putting boundary conditions at infinity, but that's a fake. The reason that's a fake is that once you reach pure flat space, once your solution cannot tell that there's a black hole anymore, if something's outgoing here, it'll continue to be outgoing at infinity. So where is the effective boundary condition of outgoingness put? It's put where the metric becomes effectively flat. In a finite number of dimensions, we'll come to that largely in a bit, but in a finite number of dimensions, this is some region of size of order, the Schwarzschild event, the Schwarzschild radius. Okay, this is of course, let's say, I don't know, 100 R0, something like that. Some number times R0, large number. This guy here is at R0. So what you've got is an effective box whose size is set by R0. Okay? Moreover, your boundary conditions are not reflecting boundary conditions. This is visually obvious. Okay? If you put boundary conditions that allow things to leak out, you get a non-Hermitian wave problem. And this non-Hermitian wave problem allows you eigenvalues, frequencies that are not real but have imaginary components.
That means the effective gravitational force beyond 100 L0 is zero?
Not exactly zero, but it's very small. That is, that the amplitude for something that is outgoing at this point to become something ingoing at infinity is extremely small. The potential barrier has died off. It's power law, so there's no precise place to say where. Okay? But approximately, it's in some large number times R0. R0 is the only length scale in the problem. Exactly, which will get smaller and smaller as you take this larger and larger. Okay? So, if in any angular momentum band, if you fix a particular angular momentum, you will get a bunch, you've got a particle in a box problem. You get a bunch of quasi-normal mode frequencies. There's only one length scale for the problem, that's R0. Okay? And so your omega, okay, will be set by 1 by R0. times some integer, some function of some integer. The first harmonic, the second harmonic, the third harmonic, blah, blah, blah. And this function will have a real and imaginary part. For an uncharged Schwarzschild black hole, you can demonstrate, and it's intuitively obvious, that the real part is such that it always corresponds to decay, not exponential growth. Okay? So that this describes the settling down of black hole in exponentially fast, because of these imaginary modes, into its natural ground state. These are the modes relevant to describing. These are what quasi-normal modes are for flat space Schwarzschild type black holes. Any questions about flat space quasi-normal modes? This was an interlude. We're going to go to ADS now. But questions, we'll need this by next lecture. Questions or comments about this? Okay? Great. Now let's turn to ADS space. In ADS space, the Penrose diagram of an ADS Schwarzschild black hole looks somewhat like this. This region is R equals infinity. Okay? This is the singularity of the black hole. These are the event horizons. And the classical problem of solving Einstein's equations in this space requires you to specify boundary conditions. Okay, the classical problem is ill-defined without specification of boundary conditions. And there is the natural boundary conditions that we will adopt, natural from the point of view of the ADS CFT correspondence at least, is to demand that this metric, as R goes to infinity, dies off, very quickly starts approximating the metric of ADS at infinity up to corrections that scale like 1 over R to the 4, as you see from here. This is an example of an asymptotically ADS solution, a solution that obeys our boundary conditions. One that is ADS at large R up to corrections that scale like 1 over R to the 4. Okay? Why 1 over R to the 4? I would have to get into more detailed discussion. Fine. Please. Will be discrete. But in any angular momentum channel, you get a discrete set of modes. Okay? Each of which will have a real part and an imaginary part.
Why should it be discrete?
It's because the effective size of the box is finite. Suppose you were doing a Schrodinger problem with a box of length L.
We're not doing any quantum mechanics.
No, but you're solving a wave equation. You see, this business about getting the spectrum is not really a question of quantum mechanics, it's property of wave equations.
So if something, in a hydrogen atom, classically, something is falling inside, you expect all.
No, you expect, it's true. You know, what he's getting at is that you expect things to settle down. That is consistent with this, except that this Fn will not be real. It will have an imaginary part. It's not a self-adjoint operator. And the imaginary part will describe the settling down. So you'll have discrete things with imaginary parts. Yeah, as somebody said, think of the electromagnetic field in a box. Just mathematically, that's the kind of problem you're solving, except with different boundary conditions. That gives you this imaginary. Okay, excellent question. Other questions or comments? Please feel free to ask. We have a lot of time. We've got 3 1.5 hour long lectures. We can do these lectures in a way that everyone can understand.
But in case of ADS, there are 2 parameters. One is the cosmological constant and also the R naught.
The cosmological constant and R naught, yes. So let's say we use units in which.
You are going to assume cosmological constant is very large.
Well, I'm going to use units in which. Well, I'm going to use units in which the cosmological constant is just 1. Okay. Now the frequencies are still set by just 1 parameter because of the scale invariance of ADS. It's a parameter in the theory, but TRJ's point is that it sounds like there's a ratio of 2 numbers. Okay? The ratio of 2.
One is large and one is small.
Yes, so it's true. It's a ratio of 2. The ratio of the 2 numbers, which is this R naught by cosmological constant. Let's use units which cosmological constant is 1. Okay? Now, in such units, we will still see that we can predict the R naught dependence of quasi-normal modes simply because of the dilatation invariance of ADS space. Okay? Let me say that immediately. I've presented here solutions, like a 1 parameter set of solutions, parameterized by this parameter T. But in some fundamental sense, I've only got one new solution. Why is that? Sorry? T is a number. It's a constant. It's actually, I've chosen to parameterize it by T because it turns out to be the Hawking temperature associated with this black brain. Okay? But from the point of view of general relativity, there's only one new solution. Why is that? Let me make the following diffeomorphism change. The following change of variables. Xi goes to xi, lambda xi. T goes to lambda t. And r goes to r by lambda. Okay? This change of variables changes this solution to the same solution by t. Oh, I even said this wrong. This was to the 4, and when I said RH was at pi t, it was really RH is at pi t. So the typo was in the wrong place. Yeah, that's what dimensionally wrong. Sorry. Okay. Okay. Yes. So this changes the solution in a way that it takes t to t by lambda. Okay. Because of that, you can completely predict the t dependence, of course, of quasi-normal modes. Okay. Good. Other excellent questions. Okay. Excellent. So now let's continue with our diversion and study quasi-normal modes in ADS spaces. Okay. So as I've said, we've decided to study this problem for many points of interest with boundary conditions that demand asymptotically ADS spacetimes. Does everyone understand what I mean by asymptotically ADS? Approaches ADS, approaches that metric up to corrections that scale like 1 over r to the 4. Okay? Now, if that's all I do and I don't have anything, I don't have matter fields or something to throw in, this is the solution, you can't change it. How do you kick a black hole in ADS? You kick it by allowing yourself to change your boundary conditions, but for a little time. That's the analog of throwing something into the black hole in flat space. So suppose here, for a while, I allow some different boundary conditions. I won't go into the details of how and what you can do, but you can imagine that allowing different boundary conditions allows stuff to create stuff, let's say gravity waves, that will fall into this black hole. But I make sure that I stop changing the boundary conditions from this time onwards. Okay, time t equals 0 onwards, my boundary conditions are kosher. Suppose I'm interested in studying the problem from time t equals 0 onwards. Okay, then I have my ADS boundary conditions. And I have to have all modes going into the horizon. So now I know what boundary conditions I should impose to study quasi-normal modes in ADS. I should impose that the modes are asymptotically ADS. They die out in infinity. That's one boundary condition. That's the analog of outgoing at infinity. Okay? And I should impose that they're ingoing at the event horizon. Okay? So now I've told you everything you need to know. The rest is technical. You just have to take Einstein's equations, solve them subject to these two boundary conditions.
So there is no outgoing mode at infinity.
There's no outgoing mode or ingoing mode. I mean, this is like Dirichlet boundary conditions at infinity. Okay? Now, in this problem, because of the little discussion we had with about the what could set the frequency of quasi-normal modes, okay? Using this kind of diffeomorphism, you can relate quasi-normal modes of black holes at different temperatures to quasi-normal modes of temperatures, black brains at temperature 1. Okay? So you can argue that all frequencies come with a factor of t outside. So it's t times some f of, but now f of what? Of course, there's f of n. But this is the crucial point. There's also k, which is the wavelength in space. Okay? In the study of the Schwarzschild black hole, we just had discrete angular momentum because the sphere was compact. Here we've got a continuous mode because the space is infinite. And because of this, we can ask, does something interesting happen? Okay, does something interesting happen? Okay, and this scaling also tells you that it's a function of k by t. Okay, so does something interesting happen when k goes to infinity? Sorry, k goes to 0, when the wavelength goes to infinity. We're looking for the long wavelength dynamics of this mode. Okay, so if you study the dynamics of you study this quasi-normal mode problem in detail, and people first did a lot of numerics before understanding the physics of it, what you find is the following. Okay? These n modes, by the way, are still the number of harmonics between horizon and boundary. But there's also k. So what people found was the following. What people found was that for generic n, as k goes to infinity, you get nothing very interesting. You get something of order t with some numbers. Those numbers depend on n. However, there are 4 special modes for which this f goes to 0 as k goes to 0. So I keep saying k goes to infinity sometimes. When I say goes to infinity, I mean wavelength goes to infinity. K goes to 0. Sorry about that. Okay? So these are modes for which f goes to 0 as k goes to 0. These are what physicists tend to call zero modes. Modes that don't oscillate if you don't make them wiggle in space. Is this clear? Okay? Turns out there are 4 zero modes. Now this is a hallmark of an interesting result. I mean, this is an interesting.
In all dimensions?
No, 4 it's actually d minus 1. If the number of space-time dimensions is d, the number of zero modes is d minus 1.
In 3 dimensions, in black.
Now 3 dimensions is special. Actually, maybe
Because I
in
know the solutions exactly there.
yeah, 3 dimensions is very special because gravity is so
There are no
special.
0 modes.
Yeah, well, I'm not even. Yeah, is that right? What about these boundary gravitons? 3 dimensions is very special. Okay, 3 dimensions is very special because there are no propagating gravitons in 3 dimensions. Let's restrict attention for d greater than or equal to 4. Okay, 2 dimensions is even more special. Okay, yeah, we won't. Those are not. Yeah. Okay, so right. So in 5 bulk dimensions, we get exactly 4. Well, d equals 2 is even more special. Even more special. Yeah. You know, there are some excursions in D that have a hope of teaching you something about D equals 4, and some excursions that don't. 2 and 3 don't, because there are no gravitons. That's roughly what I want to say. So let's not consider those cases. Okay. Fine. So there are exactly 4 zero modes. For the zero modes, for 2 of the zero modes, the answer that, so now when you've got 0 at k equals 0, you can ask what happens as k goes to 0. Okay? And for 2 of the zero modes, omega goes like t into kt. So like k, actually k by, I know this number, by square root 3. Okay? And for the other 2 zero modes, omega goes like t into kt, k by t, the whole thing square, so, with an I actually. So I k squared by t, and I don't remember the number, it's not important. Okay. Now, zero modes are often a sign of something interesting. Why is that? You see, when you've got a zero mode, see what we've got is a lot of stuff, okay? Because for every n, we've got a mode. Got lots of these quasi-normal modes, but all of them have a certain mass. I'm using the word mass loosely, certain omega, which is set by t. However, the zero modes have an omega that can become as small as you want. So, in such a situation, you have the possibility of getting an effective theory of the zero modes that remains local even after you've integrated out all the non-zero modes. That effective theory should be simpler than for all of gravity, because it's a theory of a small subsector of all of gravity. It's a theory of just the zero modes. It's the kind of philosophy that we use all over physics, right? Okay, this physics, philosophy of decoupling of scales. If you've got something happening at very low scale, stuff at high scales can be integrated out and get new effective theory at the low edges. So, but you see, because black holes are thermal, this is an unusual situation. Kind of situation that's not very often been encountered before. Question you can ask is, what is the effective long wavelength theory of these low energy modes. Okay? Now, if you were interested only in the effective theory at linearized level, you've got it. It's quasi-normal modes, there's nothing to say. A bit boring. What we're interested in is not that. We're interested in an effective non-linear theory of the low energy modes. Whatever that means. I'm going to tell you what it means in a bit. Okay? No, there is not a topological argument, but there is a Goldstone argument that I'm going to give you just now. Okay. So in order to get to this effective non-linear theory, as TRG suggests, we should first try to understand why do these zero modes exist. Usually speaking in physics, if there are zero modes, there's a reason. Okay? Where did the zero modes come from? It is. Give 2 minutes. Boosts it. Yeah. How am I doing on time, by the way? This is 40 minutes. Great. Okay, great. Okay, so maybe we'll have the whole first lecture on fluid gravity. 1.5 hours is okay? Is really okay? That's what you intended, right? Okay, great. Yeah, we can have the whole first lecture on fluid gravity, and then the next 2 lectures on large d. Okay. So, great. So where were we? So when you've got zero modes, you should be asking, why are there zero modes? Now in this case, the reason for them is quite obvious once you start thinking. And the reason goes as follows. Look. This solution here that I've written has a parameter in it. That already tells you should expect 1 zero mode. Why is that? It's simply Goldstone's idea. If you've got a solution with a parameter and you've got long wavelength physics, then you can take a configuration in which that parameter varies very slowly. When that parameter is not varying at all, you'll get omega equals 0 because it's a solution. So when it's varying very slowly, you'll get omega small. If there's any locality in the world, Einstein's equations are appropriately local to make this true. Okay? That explains one of them, but what about the other 3? Is this clear? What about the other 3? Well, perhaps it's the same thing. Perhaps there are more parameters. We just haven't thought hard enough about it. And, of course, that's the case. That's the case because, who told you to choose t as the special coordinate behind which you put r squared minus 1 minus pi t, the special factor? What about your friend who's boosted with respect to you? If he chose his t, you would be doing something different. Okay? So clearly this is not the most general solution you can write down. How do you write down the most general solution? You write down the most general solution by boosting this. Or by writing this down in a way that is Lorentz, whatever it's called, covariant. Okay? So let me define u mu to be equal to -1 for this solution, to be -1, 0, 0, 0. Okay? I put a -1 because then when you raise it, it'll become +1, it'll become a fall velocity. U squared is -1. Okay? Now, I can write this in a way that looks sort of covariant as follows. Define p mu nu, the projector orthogonal to the velocity, as eta mu nu plus u mu nu. Okay? If you wrote this out as a matrix for this particular u, this is simply 0, 0, 0, 0, 0, 0, 0. Just erase the time part. It's projector onto space. Okay, I'm using mostly positive signature. Okay, then that metric can be written as ds squared is equal to dr squared or r squared. This doesn't change. Minus r squared into 1 minus pi t by r to the pi t by r to the 4. And now I want to write this in terms of this u. Well, that's easy. It's u mu dx mu. The whole thing squared. And then plus r mu nu, r squared times p mu nu. Dx mu dx. This is the same metric. just written in terms in fancy language. That's this dxi squared. That's this stuff. Once we've written it this way, all that this metric can care about being a solution to Einstein's equations, is that u is a constant and u squared is equal to -1 because everything else is a choice of frame. So any solution with a constant u such that u squared is equal to -1, any configuration like this, is a solution to Einstein's equations. Exact solution. Okay? And now what we've got is 3 parameters in u. Because u had 4 parameters, it was 4 velocity, but u squared was -1. And we've got 1 parameter in t. And we can play this Goldstone game, both with u as well as with t. Okay? And that is the reason we had 4 zero modes. Is this clear? Okay? Please. No, you see, we're going to get real imaginary, doesn't matter. It's a question of first order. We're going to get 4 solutions for omega, which will have a real part and an imaginary part. But it's just 4 modes. Sorry, maybe I didn't get your question.
Is there a way to understand
why there's an imaginary part?
No, why the leading order is real for the first two and imaginary for the
Yes, there is a way to understand it, but that will come by the end of the lecture. It's because sound waves have real frequencies and shear waves have imaginary frequencies. That's the answer, but what the relation to sound and shear is will come. Hang on. Okay. Great. Other questions or comments? Okay, fine. So now we're in business. We understand why there are these zero modes. Now, there are 2 kinds of understanding. One is, okay, you understand something and then you go home. The other kind is you understand something and that triggers something else. Okay? Of course, the second one is much more interesting. And this is the second kind. You see, once you realize that that the light modes are light modes because of the Goldstone phenomenon, or because of what I think more correctly called, because what we're dealing with is collective coordinates. Okay? This suggests something. This suggests that it should be possible to find an effective theory of long wavelength fluctuations at the nonlinear level, just by looking at the nonlinear collective coordinate description of your physics. Very much like you do for pion physics, for instance. Okay? So you have to stick to low energies, long wavelengths. But you can go to distances that are so large that even though the temperature and the velocities vary very slowly, in the solution from one point to the other, the temperatures can be, the ratio of the 2 temperatures can be very large because the small changes build up. The quasi-normal modes we looked at don't allow that. They're in expansion in amplitude. Okay? But the key point here is the simplification because of distance scale, not of amplitude. We understand this once we understand this, a Goldstone phenomenon. So it should be possible to find a nonlinear theory, okay, of stuff that varies slowly, irrespective of how big the variation is. Question, can we determine this nonlinear theory? Okay, is the question clear? Okay, answer yes. Turns out a very interesting answer, very interesting structure, the answer. And I'm going to briefly describe to you how you do the analysis to get the answer, and then what its physical interpretation is. Okay? So all of this lecture is going to be about fluid gravity and ADS. The next 2 lectures will be about flat space and large Z, the new stuff. But, okay. Of course not. It cannot be unitary. Absolutely not. In fact, the classical version of that statement is that if you try to get the equations of motion out of an action, you will have to make it kick and scream before you do it. Okay? The classical version of that statement is that what we are going to look for is just equations of motion. We will not be foolish enough to try to look for an action. Okay? However, having said that, I have to say that there is a lot of current activity on trying to find actions for dissipative hydrodynamics. Okay? For very good reason. Mukund Rangamani, Loganayagam, Hong Liu have been writing papers that attack each other's papers in the true spirit of science. On the subject, and it's a very interesting field. There's lots to say about it, but to zeroth order, we're not going to get into that.
But if you believe, let us say, if you believe that everything is coming from some quantum gravity which is changing, etc.,
Yes.
then these things cannot come from that.
Oh no, they can. It's just that you're ignoring some degrees of freedom. It's like, let me give you an analogy that's not chosen at random. It's like hydrodynamics. Okay? Hydrodynamics is dissipative, therefore does not come from an action. Nonetheless, the theory of atoms or molecules, perfectly unitary. It's like that. What are you ignoring? You're ignoring, roughly speaking, degrees of freedom behind the horizon. We come to this in a bit. Okay. What are the atoms? Presumably, the gluons of n equals 4 Yang mills. In that context. But this is a great question. That's situation dependent. You see, for the M2 brane, the answer is different from the D3 brane. Okay, this is actually it's a very important question. Einstein was able to understand. Let's get back later. Yeah.
But at this level, it's only space-time.
It's only space-time. At this level, it's only space-time. But in many of these situations, we know, in particular examples, we know the answer to Narayan's question. At least those of us who are convinced.
If you embed everything in string theory,
Right.
that may be your.
Yes.
But in principle, the hydrodynamic interpretation of space-time structures can be given independent of this.
Independent. The classical analysis purely stands on its own. Yes. We will. Okay. So all I'm doing, and all I will do except in the last 5 minutes of this lecture, is classical gravity. I'll never mention string theory, except in the last 5 minutes of this lecture. Okay? So it's just analysis of differential equations. Okay, great. Now, how do we proceed? How do we find the nonlinear low energy theory of this stuff? You see, the basic idea should be Goldstone's idea. What we want to do is to make up a configuration that locally resembles an exact solution. So locally resembles one of these branes. Okay? But whose parameters of exactness vary as you move around. And then put that into the equations of motion, and from that find effective equations of motion for the parameters. It's kind of thing Goldstone did. Okay? He worked. What? Nambu Goldstone, no doubt. Sorry, I'm sorry. The kind of thing many people do. My history is wrong, I'm sure. Okay. Okay. Yeah. So, how do we do that? You see, there's one twist in the story that is interesting. The idea of locality for these configurations is interesting. You see, because we've got long wavelength in these x directions, but not in the r direction. Things are varying on length scale 1, or more precisely on length scale t, in the r direction. So, we want things to locally look like any of these solutions in x space, but for all r. Okay? So the Nambu-Goldstone idea is to have little lumps of stuff that locally look like exact solutions. Our idea would have to be an evolution of that. Will have to be to have little tubes of stuff that locally look like exact solutions. You see? Because these tubes are tubes in the r direction. And then we're going to have to stitch together these tubes to build a configuration which will hopefully solve Einstein's equations exactly. Okay. Now we're getting to a point which is actually very important because, we've got these solutions, we've got these classical solutions. We've said we've got to break them up into tubes and then have the parameters of this equilibration vary along with your tube. Now there is a key physical question. The question is, what direction should these tubes travel in? Okay? A very natural thing to do. Oh, I shouldn't have rubbed up. I'm sorry. Let me do it here. This is u mu dx mu whole thing squared, and this is p mu nu. A very natural thing to do would be to just take this configuration and to make u mu and t functions of space, slowly varying functions of space and time, and use that as the starting point of what you're going to do. That seems to implement this idea of locally having exact these solutions. That's totally wrong, okay? That's totally wrong for a reason that is both physical as well as technical. The physical reason is that when you're doing that, you're working along lines of constant something. You know, your tubes have a certain direction. Now, if you vary r, keeping all x's as well as time fixed, then what direction are you going in this Penrose diagram? You're going from here to here. Because as all of you know, the coordinate t is infinite on the event horizon. So if you keep t fixed to anything particular, you must be hitting the bifurcation point. Okay? So that choice, just taking this metric and making t and u functions of space-time coordinates, amounts to foliating your space in tubes, all of which end up at the bifurcation point. Okay? There's something very strange about this, this thing, both technically as well as physically. The physical thing that's very strange about this is that's not causal. Your stuff here goes back in time. And this leads to all sorts of paradoxes when explored carefully. I mean, it couldn't have worked. The technical thing about this that is bad is that, you know, black hole solutions are on the edge of making sense. And black hole solutions written in Schwarzschild coordinates look like they're singular, but they're actually not, because you can perform a coordinate change to make them manifestly non-singular. But if you work in these coordinates and then change something, what you can do is to convert a fake singularity into a real singularity. Okay? And so if you wrote down this configuration here with stuff varying, what you will find if you analyze it carefully is you're not writing down a regular spacetime. I mean, of course there are singularities up here, but there are also singularities somewhere here. This we don't want to do. We want to work with configurations of Einstein gravity that are non-singular everywhere except at real singularities. Okay? Is there a way to cure, you know, the kind of thing that we should look for is tubes that go like this, okay? And is there a way of doing that? There is a way. The way is to look at these solutions in ingoing Eddington-Finkelstein coordinates, and then do this trick of making t and u functions of spacetime. That amounts to foliating your spacetime into tubes that go along null ingoing geodesics, and that works just fine. Let me just write that down. We have ds squared in null ingoing Eddington-Finkelstein coordinates. The same solution can be written as minus 2 u mu dx mu plus minus p mu nu, sorry, u mu u nu mu the singularity of the Schwarzschild metric, which came from the fact that the coefficient of dr squared went to 0, is just not there in this coordinate system. Ah, thank you. That's a dr. Thank you. Okay? It's just not there in this coordinate system. And because of that, if you change this, see, the point is that in this solution, in this coordinate system, the future event horizon, the solution, is not just regular, it's manifestly regular. Okay? So if you change these u mu's to be functions of x and t to be functions of x, you continue to have a solution that is manifestly regular. So the technical objection goes away, and physically what you're doing is foliating your space-time into tubes that run along this. Okay. It will not be stationary. We're not interested in looking at stationary. We're still looking at things that evolve, because you hit it and it evolves. Yeah. Stationary from our point of view is boring. Right? Stationary solutions we can just solve for. We want much more interesting things.
But the field, whatever field theory or the quasi-normal modes out of this
Yes.
will be described by some time-dependent Hamiltonian.
No, you see, these will be thought of as being built up, but will be the nonlinear theory of the quasi-normal modes. It's nonlinear quasi-normal modes about a stationary background, if you want to think of it that way. But this is just some time-dependent configuration. Now there are no quasi-normal modes anymore. Okay. Clearly, this is a nonlinear generalization of quasi-normal modes. Because, the quasi-normal modes, as I explained to you, came about because you had this u mu infinitesimal u mu's varying over long distances and infinitesimal temperatures varying over long distances. Here, we've got a configuration that does that, but makes these variations finite. However, this is just a configuration, okay? It's not a solution of Einstein's equations. Okay? But we know that it's a solution when the variation goes to 0. So, suppose we take u mu equals u mu as a function of epsilon times x and epsilon times, let's say epsilon times x mu. We're working covariantly. And t is equal to t of epsilon times x mu. Suppose we do that. Then what do we know? We know that where epsilon we'll take to be a very small number. By the way, what is putting this epsilon is just a counting device. But what does it mean? If I take epsilon very small, and u is a function that varies on length scale, that varies when its argument changes by, that varies significantly when its argument changes by 1. If epsilon is very small, for the argument to change by 1, x has to change by 1 over epsilon. So putting this ensures that what you're looking at are long wavelength modes. Okay? So I'm going to use this counting parameter epsilon and set up a perturbation theory in epsilon. The key point is that when epsilon is 0, this is a constant. All fields are a constant. They just don't change. And then you have an exact solution of Einstein's equation. Therefore, when epsilon is small, you will not have an exact solution of Einstein's equations, but the extent to which your configuration will not solve Einstein's equations will be small. So it's a situation that's ripe for perturbation theory. Okay? So what we want to do is to set up perturbation theory to compute true solution of Einstein's equations, starting with this guess. Just a quick interlude here. The key point about perturbation theory, which is one of the key weapons in the armory of a theoretical physicist. Certainly it's taken me some time to realize this, but perturbation theory is half an art and half a science. Okay? It's a science in once you started with your perturbing configuration, what to do after that is relatively straightforward. That's turn the crank. But the art comes in guessing what to start with. You're looking for a solution here which you think exists. You start with something here, try to do perturbation theory, good luck. You have to start with something that's near what you're looking for. Then perturbation theory works. Okay? Many very simple situations, it's obvious what to start with. Then there's no art involved. But in situations as complicated as this one, the thing that's really interesting about perturbation theory is what is the starting point about which you're going to perturb. You have to be creative about that. That's half your work. Okay? This, we're claiming, is the starting point for perturbation theory for this problem. Okay. Now, I have to set up this perturbation theory more seriously. Okay, so let me suppose that the true solution of Einstein's equation is g mu nu, which is g0 mu nu of epsilon, which is a function of this u of epsilon x and t of epsilon x. I'll just denote this by epsilon x. Okay, so it depends on x through u and t, but I won't keep saying that. Okay, plus g1 mu nu of epsilon x times an explicit epsilon plus epsilon squared times g2 mu nu of epsilon x, and so on. That's my ansatz. I'm guessing that there is a solution of Einstein's equations of this form where g0 of epsilon x is what I've written down for you here. It's the seed starting point for perturbation theory. question, can I find G1, G2, G3, and so on, so as to solve Einstein's equations at successively higher accuracy in epsilon? That's the question we're going to ask.
May not be always possible.
May not be always possible, in which case you're doing perturbation theory wrong. So that's the test.
Yeah. Epsilon going to zero will make maybe essential singularity.
Could be. Actually, essential singularities don't inhibit you from setting up a perturbative expansion often. As you know, for the anharmonic oscillator, the answer has an essential singularity, but that just means that your coefficients grow faster than is convergent. That does not make perturbation theory useless. All of perturbation theory and quantum field theory is of that form. Okay? It may be worse than that, in which case you're in trouble. But perturbation theory to some finite order doesn't easily distinguish between essential singularity and of certain kinds and not, as you know. Okay? Almost, in fact, I know that ours is of that sort. How do I know this? I know this because of a beautiful result by Yannick and collaborators. I should tell you about this in a bit, but I'll forget, so let me just say it. I'm going to tell you about first and second order in perturbation theory. Particular sector, they carried out this perturbation theory in a computer to 240th order. Okay? The thing I'm going to tell you about. Then they used that to check whether it was convergent. Of course it wasn't. Then to check whether it was Borel-Sommerville. It was. Then they could find the first singularity of that Borel in the Borel plane. And you know what it agreed with really well? It agreed with the frequency of the first massive quasi-normal mode. So, we knew that it can't be convergent because there have to be singularities. It's working exactly as well as it should.
Then in that case, you don't have to do 240 orders.
Huh.
You should do some Faraday approximation.
Sure. If you're clever, you can. Sure. You can try various things. But, this made no assumptions. Again. It was really tour de force because just roll the crank, no arguments. Okay. Okay. But let's get back to more easier stuff for a moment. Okay. We're going to try to find such solutions. Okay. We're going to try to find such solutions. Okay. Now, I won't go through the algebra, of course, because we have 10 minutes left for this lecture and we have new stuff to do in the next 2 lectures. But I want to get the main ideas across. Okay, so let me quickly go on to the main ideas. You see, what we have are Einstein's equations. They've got all kinds of indices and so on, but I'll just denote them by E. Okay? You put E and you put in this configuration, G mu nu, because when epsilon goes to 0, Einstein's equations are solved. The first thing you'll get is at order epsilon plus blah blah. Let's take these equations and truncate them to order epsilon, first non-trivial term. You'll get something here. You get 2 kinds of terms. Okay, in this. The first kind is from this stuff. This is explicitly at order epsilon. So this just comes by linearizing Einstein's equations about something because of this stuff. Now, this stuff already has an epsilon. If you take a derivative of this with respect to x mu, you pull out another epsilon. That would be order epsilon square. Doesn't appear order epsilon. So at order epsilon, whatever comes with G1 cannot have derivatives with respect to x mu. Can have derivatives with respect to R. So the structure of the first order Einstein equations will be H on G1 is equal to S1. Okay? H is a homogeneous, ordinary differential, linear, ordinary differential operator. Differential operator in the variable R. Okay? S1 is the stuff that you get because your u, mu, and t was not constant. Okay? So this will involve derivatives of u, mu, and t. It will involve one derivative. Why? Because every derivative of u pulls out an epsilon. Every derivative of t pulls out an epsilon. Okay? Structure of this equation is H and G1 is equal to S1. But this involves first derivatives in temperature and velocity. Key point is that this is linear, but it's also ordinary differential equations. I want to emphasize that. The role in life of perturbation theory for classical problems is to linearize nonlinear equations, that you get Perturbation theory is a technique in classical problems, in certain contexts, for converting a single nonlinear equation into an infinite number of linear equations. That's sort of what you expect. What we have here is that we converted a single nonlinear partial differential equation in a bunch of linear ordinary differential equations, because the perturbative parameter involves asymmetric scaling of some directions of space. That's a technical novelty. Okay, now all you have to do, okay, now you see, we've already seen that this homogeneous operator here is a homogeneous operator that has maxed out its epsilons because we've got an epsilon with G1. This homogeneous operator cannot know anything about anything else that involves variation, because that has more epsilons. In particular, then, that homogeneous operator is just the homogeneous operator of linearized fluctuations about a black brane, which is uniform and constant with the parameters at that of temperature and velocity at that point, because any knowledge of how it varies away from that point is at higher order than epsilon. So this differential operator is a very simple one. It's the same differential operator you get when you're solving quasi-normal ones. Linearization about a constant uniform space brane. You get it with the source. Okay. Now, the last thing I have to tell you that's sort of important is the following. How do you, can one solve this problem? Okay. Now, you see, one or two details. First detail is that when you're solving a problem involving Einstein's equations, you need to set a gauge, set a choice of coordinates. Otherwise, you don't get a unique solution. The coordinate choice we're going to make, that we made when solving this problem, was that the dependence on r, the dr dx mu term is exactly this, and the dr squared term is exactly 0. We had 5 coordinate changes to set 5 conditions, and we did that. Okay? So that leaves us, a metric in 5 dimensions has 5 and a 6 by 2, so it's 15 components. 5 of which we've gauge fixed away, so we've got 10 components left to solve for. But we've got 15 Einstein equations, because the Einstein equations are 5 into 6 by 2, symmetric. How can you solve 15 equations for 10 variables? Well, this of course is not a property of our perturbation expansion, it's a property of Einstein equations. You can always ask this question. And the way it works is that conjugate to any choice of gauge, some of the equations become almost trivial. They become what you can call constraint equations. Okay? Constraint equations are equations that, so in conjugate, what we've done is something very special, okay? We've determined completely the R dependence of our solutions. So, all Einstein equations with an R coordinate, okay, turn out to have the following property. This you can read about in Wald's textbook, for instance. Okay? They have the property that if the other 10 equations, so there are 5 such equations, right? Okay? If the other 10 equations are obeyed, and if these equations are obeyed on any one R slice, then they obeyed always, at every R slice. Okay? So 5 of the 15 Einstein equations don't become equations that tell you how to evolve your data in R, but tell you how the data has to be constrained on a given slice in R. And it doesn't matter which slice, once you obey your dynamic. Okay? Those equations, in this context, turn out to take the form d mu of t mu nu is equal to 0, where t mu nu is a particular tensor built out of velocity and temperature. It's, for those who know ADSAF, it's simply the boundary stress tensor of this configuration. Okay? Some particular tensor built out of velocity and temperature. And the really important point about this is that, see, I'm brushing through this. We'll go more slowly in the actual problem of interest. But okay, the really important point about this is that this equation by itself has a derivative in the field theory directions. Okay? So, this equation, or these collection of constraint equations, when evaluated at first order in epsilon, do not care about the corrections G1, because they already get 1 epsilon from differentiating u's and t's and so on. Okay? If they also carry on G1, they would have a second epsilon. So perturbation theory, the equations of motion, the Einstein equations break up into 2 sorts. The first sort does not help you determine G1 in terms of G0, but constrains what velocity and temperatures can go into your original construction. Okay? Once this constraint has been obeyed, the remaining 10 equations allow you to determine G1 in terms of G0. Okay? This is the most important equation. This is the most important equation in the game. It tells you that your original perturbation theory was wrong, couldn't be generalized to a true solution of Einstein's equations unless your starting point was chosen cleverly. Your starting point was chosen so that your velocity and temperature, so I'll tell you in this context what this T mu nu turns out to be. T mu nu turns out to be number, which is important, times T to the 4 into eta mu nu plus u mu u nu 4. Okay, that's what it turns out to be. So unless you start out with a configuration that obeys d mu of this object is equal to 0, a velocity and temperature field that obeys that interesting differential equation, your perturbation theory idea was wrong. Okay? But if you start with this, you can do it. Now, this I've told you about to first order, but you can carry it out to second order. We did that explicitly, and as I said, in special subsectors, it's been carried out to 40th order. No barrier to going to higher order. What you get is that the condition on temperatures and velocities that have to be imposed get corrected order by order in epsilon. So this equation continues to be of this form, but with a stress tensor, which gets a contribution at first order in epsilon. In this case, the contribution at first order in epsilon turns out to be T cubed times sigma mu nu, where sigma mu nu is the shear tensor, times a number which I don't remember, sigma mu is shear tensor associated with the velocity field. At second order, there turn out to be 3 corrections. There's a huge story we can go on. Okay? But this is the key point. The key point is that the equations of motion break up into 2 sorts. A, those that constrain what you started with. And B, those that allow you to solve for the first correction once you know once you constrain what you started with. Okay? And you can continue this order by order and just go on forever. What is the net upshot of this? The net upshot of this is the following. In this long wavelength sector, what you've established is an equivalence between two different dynamical systems. Okay? The first dynamical system is Einstein's equations at long wavelengths about black brains, about locally black brain type configuration. Second dynamical equation, a system, is this set of differential equations. This set of differential equations lives in flat space. Okay? There's no gravity. What are the variables of this differential equation? A temperature field, a velocity field. Okay? Now, if you were doing if you didn't know any other physics, you would just say, well, that's interesting. We've got a relationship between the equations of gravity and the presence of the Earth. It's these interesting non-gravitational differential equations. Wish I knew what they were. Of course, we do know more physics. We've all read Landau Lifshitz textbooks from volume 1 to wherever. And in particular, we've read the textbook on hydrodynamics, right? Okay, I hadn't, of course, but we should have. Okay, and these are precisely the equations of relativistic hydrodynamics. With a particular, in fact, this form is forced by conformal invariance. This is the perfect fluid form of the stress tensor. The next term, the coefficient of that is what's called viscosity, shear viscosity. The next terms are unfamiliar because Landau Lifshitz stops at first order. But you can go on to 240th order and presumably more. Okay? So that's really cool. What we've done is make contact between, what we've done is just show that the effective motion of horizons in negative cosmological constant spaces is governed by, sounds incredible, a non-gravitational problem, a problem that seems to have nothing to do with black holes, problems of relativistic hydrodynamics. Relativistic hydrodynamics of a quantum field theory, of a conformal field theory. Now, in the last 2-3 minutes, okay, why should we have expected this? Of course, gravitational physicists who just found this directly would have been very surprised, perhaps, and amazed at the beauty of it all, but may have wondered whether it was just a curiosity. Actually, we know it's part of a larger story. The thing that we know about is the ADS CFT constant. We know that, for instance, n equals 4 Yang-Mills theory is dual to a gravitational theory in ADS5 space, and it's a fact that this gravitational theory, n equals 4 theory at large n and strong coupling, the fact that this gravitational theory admits a consistent truncation to Einstein's equations is a negative cosmological constant. Now, something that we think we know, or they said we think we half know about quantum field theories, is that if you put enough stuff in them and you leave them, they equilibrate locally. And they equilibrate locally fast. Timescale in this theory given by t. Okay? And then the subsequent dynamics of this theory is the dynamics of this locally equilibrated stuff trying to get to global equilibrium, and has a name. It's called hydrodynamics, fluid dynamics. It's a subject that's been studied for 200 years, including and summarized so beautifully in this beautiful textbook of Landau and Lifshitz. Okay? So, since there is this general expectation that all quantum field theories, in particular n equals 4 Yang-Mills theory, should, under appropriate circumstances, fast equilibrate and then be described by the equations of the classical equations of hydrodynamics. There's also the specific expectation due to Maldacena that n equals 4 Yang-Mills theory at strong coupling and large n, under all circumstances, not this long wavelength, but all circumstances described with the equations of gravity. 2b supergravity, but which admits a consistent truncation to negative cosmological constant Einstein equation. Put the two of them together, and you say, well, if both these deep people who know about hydrodynamics and this deep Maldacena who knows about n equals 4 Yang-Mills theory, if they're both right, then it makes a prediction. It makes a prediction that under appropriate circumstances, negative cosmological constant gravity should reduce to the equations of hydrodynamics. And that's what we've discovered independently, just by pure analysis of Einstein's equations. No appeal to strong coupling, weak coupling. It's just true. It's just a fact. Equations of hydrodynamics with constitutive relations, with dissipative parameters that are determined unambiguously by Einstein's equations order by order. First order, second order, 240th order. Okay? So, we've just answered the first question we started. This, by the way, is a big subject. It's 8 years old as we speak, and has generated many hundreds of papers and a lot of interesting results that this is not the subject of my talks. Okay? I just wanted to present this to you as an example of as the prototypical example of something I consider very successful. In this context, we have found a clean answer to this question. What is the effective dynamics of effective membrane dynamics of black brain-like objects in ADS? First question, what does effective mean? Effective means, in this case, in some parameter. What's the parameter here? Long wavelengths. Okay? The answer to this question is something non-gravitational. It's not holographic, in the sense that it lives in one lower dimension than the original problem you posed. Okay? And in this case, it turns out, beautifully enough, to be something that has independently been well studied for 200 years, namely the equations of hydrodynamics. Okay. Relativistic hydrodynamics, only 100 years. Okay, let's lower our standards. Okay. This is the prototype of what I'm looking for. You see, if you're going to get something interesting, it's too much to hope that you will be able to solve horizon dynamics analytically. Just because then, usually things you can solve analytically are not interesting. Analytic solutions don't describe very interesting physics usually. The starting point for the way that this got rounded is not by giving you a solution, not by telling you, here are all the solutions of long wavelength dynamics. It's by relating this problem to another problem. The other problem is also complicated. Okay? Problem of hydrodynamics. But it's a different problem. It's got a different set of complications. And in some sense it's simpler because it doesn't have the complications of gravity. Okay? So what we found is that in some limit, the long wavelength limit, horizon dynamics is completely reduces to another dynamical system, namely the dynamical system of hydrodynamics. Okay? Over the next 2 lectures, what we're going to try to do is to ask, is there a similar reduction for the dynamics of horizons of black holes in flat space? This whole story was very tied to being in ADS space, long wavelength, blah, blah, blah. We're going to ask, is there a similar reduction for the dynamics of black holes in flat space, so that we can address questions like the collision of 2 black holes? What we're going to find is the answer is yes. The parameter here will turn out not, I shouldn't say not to be, parameter here will be, I will explain to you, but we need a parameter, okay, we need a parameter. The parameter, what we're going to do is to enlarge our problem to studying black hole dynamics not in 4 dimensions, but in an arbitrary dimension. And the parameter will turn out to be 1 over the number of dimensions. Okay? And we're going to find, once again, that even in this limit of large number of dimensions, we won't be able to solve the motion. But we'll reduce the motion to a non-gravitational problem, an interesting non-gravitational problem, which we will describe. Okay, so I'll end this lecture here. Sorry to have gone over time. Next lecture tomorrow we'll talk about large D black holes. Of course, questions, comments.
How does this first quasi-normal mode solution start with one solution and then use all these one starting point and then all
The light quasi-normal modes to leading order are simply the derivative of these solutions with respect to u. You take the stationary solutions, differentiate them with respect to u. To leading order, those are the light quasi-normal. Now, the question of what the first massive quasi-normal mode looks like, if that's what your question is, in 4-dimensional AGS space, nobody has an analytic solution to that. It's just something you see numerically.
you start off with this constant one.
Yes.
And then you add all the non-linearity and
Yes.
it's able to see that.
Yeah,
It's like the result that you put at 240.
Yeah, you're able to see that after you go. Yes, you're able to see that. Incredible.
Maybe there are some excitations that you need to add to make it unitary or something like that.
Well, it's the usual story. What you're doing is integrating out some stuff to get an effective theory. The effective theory is going to break down at the scale determined by the mass of the first least massive thing you've integrated. That's what you're seeing. Now, you can ask, can I make a better theory by including these modes? But you see there's no mass gap between the first and the second quasi-normal mode. So if you include the first, you must include the second, then you must include them all. And we know that theory, it's Einstein gravity. So you see, the theory we started with was we knew. What we want is a reduction to something simpler. And that happens.
With the ansatz, like with the background.
No, but you see, once you include all quasi-normal modes, there's no more ansatz. It's just all of Einstein gravity. The nonlinear theory of all quasi-normal modes is Einstein gravity. So there's nothing else you can do. You see, you need this mass gap. You've got either hydrodynamics or you've got Einstein gravity, nothing in the middle. There are many papers claiming more, but it's all nonsense, in my opinion. Yeah.
So this consistent quantities which you went,
Yes.
the event horizon is still there. That's an outside.
Of course. The event
The
horizon
boundary
is physical.
conditions are still applied
At the event horizon.
At the event.
Yeah, though in Eddington-Finkelstein coordinates, the nature of those boundary conditions is more transparent. The nature of the you see, had you had something outgoing in Schwarzschild coordinates, what it would have translated to is a irregularity, a non-analyticity in Eddington-Finkelstein coordinates. So the boundary conditions you impose are just that everything is smooth. So it's almost not a boundary condition. You see, it's just the condition of regularity at the event horizon, regularity everywhere. This is actually sort of important because you might have been wondering
The
since
mode
the
is
event,
continuous and the first derivative is also continuous.
and actually completely analytic. As a function, it's analytic. The boundary conditions you would impose without thinking. Just anytime you see a singularity, drop it. That's the only boundary condition. This is actually quite an important point because where you might have been leading is the question of course, where the event horizon is depends on the solution. And it's a complicated question. So if you have to impose a boundary condition at the event horizon in a nonlinear problem, that sounds like a very difficult thing to do. Because you can write something down, but that RH is, yeah. You understand, right? I mean, the great thing about these coordinates is that you don't have to, you impose the same boundary conditions everywhere. That's just a regularity. That automatically does it. It's actually a fantastic set of boundary coordinates for this problem. And as you will see, we will hit upon another fantastic set of coordinates for the next problem. These other fantastic coordinates have another name. Again, a name I never heard of till we actually invented the coordinates. The first time I gave a talk on this, somebody told me, you're working in Kerr-Shield coordinates. We're going to work in these Kerr-Shield coordinates in the next thing. Again, they're fantastic for that problem. As I said, in perturbation theory, half of your victory is in choosing the starting point. My other bit of advice for the younger people here is in a classical gravitational problem, half of the victory is choosing the right set of coordinates. No. Well, you see, there's a one-to-one correspondence. Once you've got a motion of the fluid, this procedure gives you a solution of general relativity. So in some sense, it completely determines the, but, so it's a bit ambiguous, that question. But there is a rough answer you can give. The rough answer is that it's the motion of the event horizon. You see, the event horizon ripples around. Its height maps roughly to the temperature. And how fast it's moving maps to the velocity. Now, I will find it hard to make the statement entirely precise, but there's something about this that is true. So, that's why what we're dealing with is the effective theory of the event horizon. Roughly speaking, yeah.
Whatever you did here is completely classical.
Completely classical.
So, how can you say that the black hole is thermal?
Okay. How can I say the black hole is thermal? You know, from my classical analysis, I'm not saying this. I just import the knowledge from the wise people who have told me it's thermal. Well, you see it's thermal in the following. Firstly, you hit this black hole and it tends to equilibrium. See, this is one of the, this is not phase-space dynamics. Volume and phase space will not be conserved. It's dissipative dynamics. Secondly, what you hit upon is the equations of hydrodynamics. Hydrodynamics is thermal physics. Okay? So already from the answer you see it. Now, the things about Hawking radiation and that kind of thermal. Oh, by the way, the other thing that you see here is that there is an entropy function that always increases. Hawking's area increase theorem is a classical theorem of general relativity, applies to the system we're looking at. And we can use that to build an entropy current that always increases. Let me just tell you, okay, when you generalize this to include charge, I haven't had the time to tell you about that, but a large D story I will. When you generalize this to include charge, my students wrote a paper generalizing this to include charge and got a constitutive relations for the charge current. And then Sohn, this physicist at the University of Chicago, for whom I have the highest admiration, wrote an email to my students saying it looks like a very nice paper, but it can't be right. Because Landau-Lifshitz have classified the equations of hydrodynamics that admit a positive divergence entropy current. And your equations don't appear in their classification. And then we went and looked at Landau-Lifshitz, and indeed Sohn was right. There was a term in our equations that didn't appear in Landau-Lifshitz. However, we had Hawking's area increase theorem, and we had used that to construct, though we hadn't published that at that point, we had used that to construct an entropy current in this problem, that because of Hawking's area increase theorem, without any details, we knew for sure that it was always positive divergence. So that's what we wrote back to Sohn, saying, too bad for Landau-Lifshitz. And actually that's how it turned out, okay? Landau-Lifshitz had made a few assumptions that were not general enough. You generalize the assumptions, you get a larger set of hydrodynamic equations that continue to have positive divergence where entropy is always locally created and not destroyed, but in a way that exactly agrees with what we found from fluid gravity. So what I want to say is that is a sure classical indication of thermal physics. Entropy is continuously being produced. That's one of the basic dynamical ingredients that is somehow behind all of this. That's one classical ingredient of it being thermal. Of course, even though let me stop that.
Also, I have another question.
Please. You can do everything. Sure. You see, what we have is a velocity field. Now, rotation is some property of that velocity field. All of that. Any configuration of hydrodynamics fits in here.
And that is the motion of the
Event horizon, yes. 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 Now, the next question is going to be, can you describe turbulence? The answer to that is nobody's successfully done it analytically. Actually, there have been numerical simulations again. People who have done simulations of hydrodynamic turbulence and simulations of the fluid gravity equations, just to check whether fluid gravity continues to work in situations as complicated as turbulence, and they find fantastic match. But unfortunately, it's not like we find it easier to understand turbulence from gravity than from hydrodynamics. So nobody's won the $1 million yet. But it's there. Correct. No, it does not. You see, there is a sense in which all the structures we're looking at live at infinity. It's a very good question. There's a sense in which all the structures we're looking at live at infinity. And Einstein, the diffeomorphism invariance of Einstein's equation becomes sort of trivialized at infinity because space is frozen to be sort of flat. You know, this question you could have asked more generally about the ADS-CFT correspondence. The ADS-CFT correspondence relates a field theory of the boundary to gravity in the bulk. Gravity has diffeomorphism invariance. Does this translate to something like diffeomorphism in field theory? And the answer, unfortunately, is no. It just doesn't give you more than what you already knew about field theory. The key reason for that is that space gets frozen at infinity. And so, yeah. Of course, it does tell you that the field theory and the hydrodynamic can be formulated on an arbitrary frozen background space-time. But that's all it tells you. Other questions, comments?